Okay, so let's start again. I have one more thing that we're going to do on the modeling side, and that is a graphical component level modeling on Modelica before we are switching back to a little bit more theoretical exercises. And so what I want to show first here is a small, simple mechanical system that I'm creating using the editor and showing how you simulate that, and then extend a little bit, and then you are going to do your own mechatronic system with a DC motor and some mechanicals, and then in a PID controlling that. So, and you don't need to know too much physics because it's a little bit more plugging things together, but it illustrates kind of the idea. So let's see here. So we can start here. We should create a new. So control 2. Just have some. Let's call it 2 because I think I got one already. So I created this model, control test 2. But now I'm clicking on this one instead of the code here. So, because we're going to use the graphical editor. And this one. I'm going to change here a little bit so we got a little bit bigger. The white. Didn't change. Okay. So here you see here is the model that we use before that we have created. Then there are some different libraries here on the left hand side. And Modelica here is the standard library that is shipped with different versions. So there are different becoming a new library every year or second year. It's like a standard. Which is updates with new libraries. And if you open that, you see here it's kind of a hierarchical set of components here. See here you have blocks. That is a little bit more state input-output blocks, kind of simulate kind of style of modeling. And you have all sort of continuous, you look at maths, things, gains, inverters, multipliers, different sources and so forth. In the state graph, this is actually the question. I have never tried this one. I've not tried now, but it might be that I have implemented the state machine for the latest versions. I'm not sure about that. We are going to mostly look at some of the blocks and the electrical and the mechanical. So let's start with creating a small DC motor, that is an electrical motor with direct current that is driving a mechanical component that is rotating. And for that we need the ground within the electrical circuit here. We need a resistor. We need an inductor. We need some constant voltage with direct current. We go to sources here. Constant voltage. I can rotate it, control R, I thought. Yeah. Zoom in a little bit. We want to, now in the first thing we want to have this direct current motor to drive this shaft, and then it's called this EMF component, which is an electromotoric force that is converting the electrical energy to rotational energy. So I'm just showing that. This here. I'm just dragging out the components first before connecting our configurator. And then we have you can combine this together first. So here, connecting.
So the top one is a resistor, right?
Top one is a resistor, that is an inductor. It's a constant voltage, having a ground there. So if we just put on some values here. 10. So this is, if you know what you're actually modeling, you should have some correct values here. So I'm just giving some whatever values that are kind of reasonable. But, so we get an effect of it. But it's typically in DC motor, this is a simple model of a DC motor. We can take the example.
On the left is a capacitor. On the
This one?
no, on the left. Or yeah.
That's the this is the voltage source. Constant voltage. It's under sources. Are you trying to create it at the same time?
Yeah.
Under sources here.
Okay.
So then we want this to drive something. So we let's put in an inertia. Then that we go to mechanicals. Here, there is a number of different. You see here, translational, rotational. These are one-dimension mechanical. And then you have this multi-body, which is a 3D-dimensional libraries. So take this rotational here. We want to make this shaft spinning around. And we got a inertia here. This. And we connect that one. And we give it a value of 0.1. So this is basically how you can model. And if you look inside these components, new class, the resistor, here is the, now I've looked at the graphical view of the inside. If you click on the actual content here, you see the resistor, model resistor, and then you see here you have Ohm's law, you see V equals this R actual times I. And R actual is defined as this a little bit more complicated. It's because it's also got components about heating. So it's got different resistance depending on the temperature. So this is a little bit more general if you're using these features. Otherwise, it's some standard value. But as you see, under each component, the leaf components, you have the actual source code, and you can see how it's defined. So there are no hidden information.
And so the annotation is part of the standard, or
some of it, getting more and more. So, for example, some of these annotations are part of defining how the graphical.
yeah.
So the annotations are actually specifying how this graphics is drawn.
Okay.
So how the symbols look like, that is part of the library. So that's why it looks kind of similar in every.
Okay.
They're trying to standardize more and more of these annotations. Okay. So should we try to see if we can simulate this? Take a bit longer. Oh, I haven't seen. So in general, I would say that people that are using Modelica for modeling is that the ones that the end users are mostly doing graphical modeling, if they're not very advanced users. Whereas library developers are mostly doing textual. So there's a pretty big nowadays. There are a number of companies that are selling libraries. So that is the business of selling libraries. I guess it's probably similar in amount of money that is generated in the libraries and the tools. So a lot of investments are done in these libraries. And for example, Modelon is one of the companies. They are having special libraries for vehicles that they sell to the big car manufacturers. It's a standard component for a lot of things. Here we can see also a little bit of the statistics here. And see if we can get some information about them. So I have to maybe that. But anyway, so here if we now look at the components here we see the names of the different, the ground, the inductor, and so on. Let's look at the inertia. And then at the inertia, we can take a look at the A, would be the left port, and the flank B, which is the right port, as I use it. And you see here, phi is then the angle. So you see that it's kind of starting off, and then it gets into constant speed. That's why it's linear here. The angle is just counting. Not so surprising. So we have an engine, an electrical engine that's driving this. Just okay. And we get some value. Exactly if this is physically relevant and interest independent of what your model. So I mean, you need to do something that is relevant for your application. But let's just show a little bit more here. If we extend this here, we say that we do this with this spring and damper.
The model, sorry, I'm trying to replicate that. The model you put there is where it was the DC machines. No.
This one.
Components,
Rotation.
This
Mechanics.
mechanics and rotational and basics, or
components.
components. And there you find the spring as well. So now I add another inertia and a spring in between. And just give some spring value here. So I'm making this inertia a little bit bigger. So we get some effect of the, when it starts to turn this around, it will be a little bit delayed of the effect of the spring. And then the spring can get it, so we can start to get a little bit of wobbling effect. Okay, so let's see if we simulate that one. Okay, so here we see, if we look at just the beginning here, we get two kind of bumps here. You see that it's started to spin, and then the start, but then it kind of, you get the rubber effect back of the spring. So it kind of, it's still rotating all the time, but the speed of rotation changes because of this rubbering back and forth. That's why it's wobbling a little bit. But then when it comes up to a more the same speed, it gets more constant. Okay, so you got a little bit of effect on this thing. Now I'm going to do like the chefs do in the TV programs and open up already there. Here we got it. So here is a complete control system where it's the same as I modeled before here, this spring damper, but here we have a speed sensor, which is basically just a convenient way of getting from this acausal port out one value. So this now here is an arrow, so this is a direction. This is input output from this. We have a sensor that is measuring. And then here I have a step, so it's basically a step after some time, changing this to a value. Now I think it's 1. Put it back to the feedback, and then I have a PI controller here. That is, and then switch to a signal voltage. So it's a voltage that is decided on the signal, how big the signal input is, that much. That is the voltage that means.
So the arrows are causal.
Yeah. So what happens in Modelica is that when you have causal directional in a connection, is that there is a way for the compiler to check that you cannot connect several outputs to one input. That would be illegal. You can have from one input, one output you can go to several inputs. So that is checked at compile time. But in the end, it's still just equations. So in the end, you have equations, and equations have no input and output. So it's the equation system that is generated in the end. So it's actually there are no inputs and outputs, but you get it as a user. That's how it's done.
It's a way to display the things that, and then when you get the equations in a way that.
Right. And it's also when you have these components that are built for inputs and output, you get the balancing correctly if they're used in the right way. If you would do that just with acausal, you can get very strange. That you can connect things together and you get equation systems that cannot be solved. So then now I showed you a little bit how to draw and do these components. So it's basically, I mean, the challenge here is that you need to be a mechanical engineer or electrical engineer and understand what you're doing, basically, and what you're modeling. That is the domain for the expert that is trying to model, and that is not the point to teach here, but to just get a feeling of what you can do. So the last modeling exercise is basically for you to do this and get a simulation result to do the whole control. Should be pretty straightforward.
Yeah.
As long as you can find the components. I can also write out some of the values. I'm drawing this sensor here. Here is the step. You can have other numbers here as well, but I just configure this so you get some sort of interesting, something that looks reasonable when you're simulating. Readable? That's the final thing you need a computer for.
It's up to define the blocks. So that's
Yeah, right. So I can give you, let's see. So the PI block is in blocks of continuous. Just ask if you
and the generator on the right of the PI is
Hmm?
the generator on the right of the PI.
It's a signal block.
Right, it's a signal. And it's under sources.
It's possible to find the other.
The feedback, you mean the
Yeah.
that one is in blocks.math. This is not obvious.
Is that feedback?
The sensor is the sensor.
This is the angle sensor.
Well, it's possible to find the step.
The step thing is in block source.
There are already a lot of blocks. It's a quite a huge library. So
It's not so
it's
block.
a really get a lot.
Yeah, but I mean, I don't know how many people are working on Modelica. It's 1,000.
Oh wow, that's good.
So I mean, and this standard library is been developed in different times. It's 97 sources.
Ah, yeah, it's
like result efficient. And a lot of companies, well,
Yeah.
getting it in the drones. But yeah, everybody is free.
So those standard libraries are the same which I get came from D1 and because they are the language.
It's part of the
Ah, see,
they are all local.
Okay, that's good.
Yeah, I think that is one of the key things.
Use it because they are the only use number of models. So it's the solver which is good.
Right, I mean, this group really is, but the
Quality solver
yeah,
quality. That's
and sometimes we edit it. Now actually, this at the beginning, we look over time, but not the say,
okay.
it's not that. That was not
Okay.
I think this now is actually pretty good.
Yeah.
But that for a long time was also no one had it.
Yeah.
But it's easier to get into
Yeah, depends on what you're expecting. Yeah.
or at least you don't need to specialize people.
Yeah.
It's easy to hire something.
That's true. What about parameters? Should be.
So that's what I wrote on the. I say it's
okay.
read from here, so I can repeat it if you want. So the step here is that I'm just saying the step size height of is 1, and then I had 20, so it waited 20 seconds.
20 is the start time, no?
Start time, yes, 20. And then I had for the PI, T is 100K 4.
What we should observe from simulation.
So what should we observe? That's a good question. So what the PI with feedback controller is that we are basically trying to stabilize. We are measuring the velocity from the rotation, and we want to control here with the feedback so we get the right currents. So from beginning at 0, and then we stop at 1. We want the control so fast as possible to go up to 1.
So the J are 0.1 and 0.8.
What do you say? The
J.
right 0.1 and 0.8, and the spring factor is 0.01. And the resistance was 200, and inductance was 0.1. And the EMF here, constant, is just is 1. Do you get something?
How long should we simulate?
I think I had 120. No, it's either 500.
500. Yeah, it's the transitory speed which is going.
100.
Right.
Yeah, it's okay.
You had a 160, yeah. So look at the angular velocity.
Oh, then we'll use it. Is it? Velocity? No, this is a kind of omega.
This one? Something like this.
The other ones.
Scale.
Yeah. If you just make it a little longer.
Okay.
This looks a little bit strange.
Yeah.
If you do 200, then it's even from 500. That's amazing. But here.
Okay, then it's and
the long run it converges to one.
It converts to one.
Yeah. But there is still some overshoot.
Yeah. Yeah, so the PI controller is not fine-tuned correctly.
Yeah.
I picked some values with that. Go, and then we should look at something else. Was it the... And then we do the... Here you go, the speed sensor. You get something similar to that?
Yeah, it's a lot of it.
No, I looked at the speed sensors. Angular velocity.
Oh, the speed sensor, okay. Out of the inertia law.
Should not be anything.
Okay, the speed sensor is the same.
It should be the same. See, let me guess. And then we should interpret what it doesn't.
Yeah, but when we have the speed sensor block, we are not modeling any kind of filtering of the sensor. I've seen the speed on the second inertia and then on the speed sensor, and it's the same. So it is assumed that the sensor is able to capture the real evolution of the speed and no low pass reaction.
Don't you get the same value?
Yes, it's the same, but
Yeah.
in practice, the sensor cannot capture on the exact behavior of the speed evolution.
No, but this
It's
is
not simulated.
but it's still the model. So it's the model is that it simulates and gets the speed out of the inertia.
So it's an ideal.
It's ideal.
It's an ideal speed
It's
sensor.
always
Okay,
like that.
okay.
So if you can have, for example, this is the same if you have a diode.
Yeah,
Yeah,
okay,
they are-
okay.
Goes directly, but that is not there.
I was thinking that was a kind of modeling of a real.
I think there might be most people use I know models, but and then make some assumptions.
Okay.
But there are also, for example, with the resistors, you can have temperature effects.
On a Mac. Yeah, I think it's you have to
Okay.
Do you get it?
Oh, yeah.
Get some other.
Yeah, I don't know what parameters here was
Right here.
Oh,
Oh, this one I had it with 4 and 100.
No,
you have some different. So you will get some different. Depending on how you set that and then how you see your PI control, you will get. So why do we get this? Depending on which parameters you set on your different components and how you configure the controller, you get different results here. And you can of course fine tune this and so on. But what we get here, why is it looking like this? Wobbling. Why is it doing like this?
It is the control effect, which is.
Not really. Not on this one. This overshoot is the control effect.
Yeah.
But this one is the spring.
It's a spring.
It's
Yeah.
free.
The spring, right. So which makes it of course much harder to control in a good way is to it tries to speed up and then it needs to slow down and then so on. But it just to see some effects.
What about the comparison between the speed evolution on the first inertia and the speed evolution on the second? If we plot together, you see that it is like a kind of low pass effect on.
Yeah, because it takes. I mean, the first one is start to turn, take some time before the other one starts to turn. But then that turns faster, and at some point it will turn, like a rubber band. You twist it, and it gets like, just kind of gets this effect. And if you would put a damper, you would be losing up you would probably not get this wobbling effect as much. Did you?
Put 0 as a parameter of the spring is like, let's say, just to look at the evolution without the spring.
Right, this is spring factor of.
The spring factor is 0, it's like, you don't have the.
What happens? Isn't it 1 or 0? That is the. You can try it.
No, it's 1.
It's 1.
It's 1.
1, yeah.
And 0 doesn't move at all.
Yeah.
Then it's not. Yeah, it's probably the spring. One should be the spring.
One is
When it's not
not
elastic.
a spring,
Right, then it's not elastic.
and whereas 0 is completely disconnected.
We are recapturing our high school physics. Okay. Did you get it to work? Well. So that was my last example for the modeling part. So the goal was more so you have tried out some different equation-based things and some simple, but still, I mean, it's not. This is things that realistically you can do it if you want to model something with the one rotational domain. I mean, the tricky thing is, of course, to do it correctly with the right parameters and so on you're trying to achieve. So I hope that gave a little bit of flavor of what you can do with Modelica. Cool.
Using the spring, we still have no continuum behavior, but it is related to quantization of the physical model. Or not? Maybe I can show you. This is related to the quantization of the solver. Okay. 9 user. 2.
Yeah, this is probably easy just to measure once.
Okay, so it's related to quantization.
There's quantization of the output, not the solver, but well the.
Okay.
You can. Yeah, I think you can configure how many points you want to retrieve for in the same place where you need the timing. Okay. So.
Simulation setup.
Right. Okay. So let's go back to the presentation. So that was the open Modelica thing. Then the next thing I wanted to do is to say look a little bit more on the formalization of the acausal semantics here. So everyone, we're all done with the modeling part? If you had a computer. Okay, so acausal connections. So now you should be familiar with what we mean by acausal connections. These are these pairs that are going bidirectional, and in the typical case you have this flow and potential value. So I've written down a little bit of formalization of this, and the purpose is here to see what happens when you're composing models together. We didn't do that here. We just had a flat number of components that we wired together. But typically you want to compose in a hierarchy of models when you have bigger models. What does that mean from a connection point of view when you're, what kind of sign, how should you construct the equations? And there's some fairly simple rules, but it's not really obvious how they work. So that's why I made a formalization of it. And this is a port-based connection semantics and how it's done in Modelica. Tomorrow I'm also going to show another approach, which is more like a node-based approach, where instead of you have connections, you have nodes which are connecting components together. It's a little bit more like, say, VHDL is doing their connection semantics. But this is more the Modelica style. So to describe this structure, we have this tuple with the following properties. So you have M is the set of model instances. That would be the components in Modelica's language, or the objects. P is the set of ports, the connectors. Then we have this sigma saying that you have from ports to models. That is basically which port is belonging to which model or model instance. This model as a function. You have the set of port connections, connection sets. So it's basically, if you take the power set of all the ports and a subset of that. How many understand what that means? Hands up. So if you have, say, three connections, 3 ports, P1, P2, and P3. We have this, it's the set. P then. One C could be, for example, P1 and P3. Another C could be just P3. The power set is a set of all combinations. So that is, we are going to use this connections. This forms the sets of ports that are connected into a set. And then we have the final, the row here. That is the parent mapping, stating if a model instance, M here, what is its parent? So if you have a hierarchy, you have an instance of model, and then it's got a parent. In the end, you have this top element, which is basically top of everything. So this is how we try to model parent. See here. Moses one.
I have some notes here stating the examples that I want to show. I'm not finding them right now.
So let's do like this. Instead of wasting time on that, let me take that tomorrow instead. So it's actually easier to understand in a good example. I'll do it like this. I'll take this, because I'm going to show the semantics, how it's been built together. And without these examples, and I can reconstruct in my head, but it will probably be a little bit awkward. So let's take this tomorrow, and then I will do take the next part instead with the AEs and start on that. Right. Okay, so just some key takeaway points from the first part here is that what you should remember about equation-based object-oriented languages is that one of the key points is reusability, and hopefully that was pretty clear. It's pretty intuitive and simple to use when you're combining this. As long as you know the parameters and you are working in domain that is understandable, you can create pretty complicated models fairly easy. And Modelica is a state-of-the-art language today, and one of the reasons that it's getting a lot of attention is that there is a pretty big standard library. That is what you saw in the Open Modelica where you were browsing around. But there's also a lot of commercial libraries that are being developed and sold to different companies. And Open Modelica is a good tool if you want to try it out. But also another alternative is Modelica, which is a little bit more on, doesn't have any really user interface, it's more the compiler part. It's got a pretty advanced interface to Python where you can do transformation of models and simulations and use it for optimization for something. That's it for the first part. Sorry for the that I couldn't find the notes. Do you want to just go on now, or are you tired and need a short break, or? Let's go on, just sure. Okay. Okay, so the second part that I want to talk about is another more underlying things. So now we talked about the language and the high level, and this is more about ideas about DAEs and differential algebraic equations. That is basically what you get out of this tool when you transform all these equations into something that you want to simulate. You get these DAEs. And how do you simulate this? How do you numerically approximate this? And it's not just that you can throw it to a numerical DA. Like I said that it was a DAE solver that I'm using. It's not enough because many of these equation systems becomes hard to solve. It's called they have higher index. And then there are approaches to reduce the index, and there are also techniques how to transform these into equation systems that can be more efficiently handled. And that is what I'm going to talk about here. But first of all, how many of you have heard of DAEs? No. No. How many of you would say that you're confident with the ODEs and how they work? A little bit. So stop me if there are, because I will kind of assume that you understand ODEs here, and when you get lost, stop me then, and then I can try to explain more. So this is the second part I'm going to. So first I'm going to talk a little bit about basics of DAEs, what it means. It's not that trivial to understand just the meaning of it. Then we're going to have a couple of algorithms that are used typically in a compiler. Not exactly as I am going to present, because all compilers have their tweaks and it's pretty complicated. But these are the main principle steps that most Modelica compilers are using. Something is called matching. Something is called BLT sorting, block load triangular sorting. Something called Pantelides algorithm. And this method is called dummy derivatives. And after a while here, it should be clear how they fit together. But it's hard to describe directly. So we bear with me. So let's start with talking about DAEs. So the definition of a system of DAEs can be like this, in the general form. And that is basically that we have n number of variables, x, see n number of them, that appears both differentiated and non-differentiated. So here the definition here we just have first order derivative, because we can always transform a higher order into first order by introducing more variables. So here we have the differentiated variables, but that you don't have in a normal ODE is that you also have variables, if we call them y, m of them, that do not appear differentiated. So they are algebraic. That's an algebraic component of a differential equation. And then f here, this is how you typically write out a system of equations. So if you write this as a function and you have a matrix here, so this is how you typically write out all the equations. It says here that you have these different, you see the dimensions here. T is the independent variable of time. And then you have n plus m equations. And you need to have the same number of equations and unknowns to be able to solve. So note here that we are not counting the unknown, the derivative, the version of x that have a derivative, and then ones that have not, as two different variables. It's the same variable. That's why you have n plus m. You see, but you have got n and n. So you're actually looking at the unknown is the highest derivative. So in the algebraic case, it's the algebraic variable because it hasn't got any derivative, and the variables appears differentiated. It is the derivative differentiated version that will be the unknown when you solve the equation system. Okay. So this is basically what I said here. N plus n number of equations. So let's look at a small example. So this is an ODE, and it's also called an initial value problem. And it's an initial value problem because we have an initial value condition specified. And this was the equation that we saw in some Modelica model as the hello world example. So why is it an ODE? Well, we have one variable, x, and it appears differentiated. So there are no algebraic variables. This is a simple ODE. In this case, the question is this an ODE or a DAE?
DAE.
It's a DAE, and the reason is we have one variable differentiated, x, and one variable that is not appears differentiated, y. But we have the same number of unknowns and equations. So now that this corresponds with x and y here was just a coincidence. This is actually a vector of variables in this definition. Okay, we have one variable, each, and two equations. Take this example further here. So is this the initial value problem? IVP. No, it's not, because we haven't given any initial condition yet. So together with this is the initial value. Well, we need some value for y as well to start with. 3 maybe. What you have to need to check here is that now, for example, x and y here, you see here, this is an equation. Does it hold? X times 1 and 3. Yeah, it holds. So this equation holds. And this equation holds because this is an unknown. So it gets solved here. So we can see here what is the derivative at point 0. What is the derivative at point 0? 2. Right. So this is a consistent initialization of this DA. This is one example of a consistent initialization. 1 and 4 would not be consistent, because then this equation will not hold. Right. So depending on the values here on the DAE, the initial condition might hold or not. An ODE you can basically put in whatever, because of the unknowns, as long as it's got explicit ODE, when you have the derivatives on the left-hand side, whatever you put in for the values of x and y, you will get some value like we did here. But the DAE have a constraint that needs to be satisfied. This is also maybe the intuition that it's a little bit more difficult to initialize DAEs than ODEs. But we can also see that -3 is also valid initialization. Because we are squaring y, if we said -3 or 3, both of them are consistent. So we get this effect because it's nonlinear. So if we would simulate with equal to 3, we get this behavior for x and y. And if we start with -3, we get this behavior. Two different traces. But both are correct initializations of the DA. And this is important to think about when someone is modeling. It's not just to throw in these components, because typically components are nonlinear. And depending on how we initialize them, maybe you get a totally wrong result. That was not what you were intended, but you get the result. But is this really what you wanted? That's why it's not just, modeling is not like a video game, you just throw in some stuff, but you need to actually know what you're doing. Okay, any questions about this first? Okay, let's continue with this example. So can we find an order that we can solve these equations? First of all, what is unknown here? This is when you're connecting equation systems to an ODE solver, the unknowns are the derivatives. So basically, if you write it's called an explicit ODE, you have the unknowns on the left-hand side and the rest of the equation on the right-hand side, and then you basically solve for the derivatives. And then it's one step in 2D, and then you have some approximation techniques, for example, Euler or Runge-Kutta or some other solver library. But whenever you have these libraries, you need to have the equation system that is doing this computation each time step. So unknowns here are the highest derivative. In this case, x dot is the highest derivative, and y, since it hasn't got the derivative, it's also the unknowns. We have two unknowns. So we can then, for example, have these steps here. We solve for y in equation 2. Why can we do that? Well, I said it here. X is known. Remember that it was just x dot that is the unknown. And then we have y, we can put it in, and then this is all x is known, y is then known, and then we can solve x dot. We have a strategy for solving this particular equation system. This might be a little bit hard to grasp if your ODE knowledge is somewhere left on the train station. But I don't know, it's hard to explain it more, I think. I hope you can follow. So in this case, we can actually transform this particular DAE into an ODE. So then we get an ODE with just one unknown. So we transform this, solve for y, and then put that inside here. Substitute it, we get this expression. Is this correct? something more to be said about that one? The sign, yeah. We actually have two solutions. As we know, we got two solutions when we simulated this. So since we are doing the square root, we should say plus minus. We have two alternatives. And if you simulate this one as an ODE with plus, or the other one with minus, you get the two solutions. Okay, so let's take a little bit bigger example here. Is this a DAE? Yes. Why?
Z and Y are not given.
Right. But X is. So we have two algebraic variables and one differential. X and Y are the algebraic, right? Can we find an order that solves this? Maybe. And it's not that obvious, right? It's not like the form, it's just into it more. Well, it's not that easy because these ones are dependent on each other. We have Y and Z in both equations, right? So they are algebraically dependent on each other. So there is something called the semi-explicit form of a DAE. It's basically when we divide the DAE into two components. Say the ODE part, where you have everything that has the differentiated form on the left-hand side. So this is like an explicit ODE. And then you have the algebraic part. That is the Y here are all the ones that only contains algebraic. So if you can transform the problem into this form, it is basically as simple as solve as an ODE. So you can still solve it using an ODE solver, but it's a DAE. So basically what you do is that you, in each step, you need to solve this algebraic equation system. If it's linear, it can be using Gaussian, normal Gaussian, row reduction, or Newton's method if it's nonlinear. Then it depends on where you start and what solution you get. And then you have the first one step in the ODE, and then you iterate back and forth. So you need to solve the algebraic equation systems in each time step. Because you have, so in this case, you would solve this as an equation system, and then you can compute this. And then you take this time step, and then again, the next iteration, X is known, Y and Z are unknown. You solve Y and Z. You substitute in the values in this one. You solve X dot. The solver takes another step. You're back. So it's not more difficult to solve an ODE. Yes, it's more work for the computer, but it's not in principle more complex. But it can require quite a lot of, if you have thousands of variables and equations that needs to be solved in each time step. It can really be computational, very costly to do this. So it's not good when you have big algebraic loops here. There are many equations that are bound together. So then it comes to this thing about index. And if you have, this is something, if you're in this area, you often hear about this index all the time. It's not at all easy or clear. And this is actually the closest to a definition that I know about. There are some other authors that have some other, but it's a classic text from these guys. These are the ones that developed this DASL package, the DAE solver that we used. So it says that the index of a DAE is the minimum number of times that all or part of a DAE must be differentiated with respect to time in order to determine X dot as a continuous function of X and T. So it basically means that how many times you need to differentiate part of your equation system so that you obtain an ODE. The number of times you have to do that is called the index. So if we look at this, that we have example we had before, can basically said to be an index 0 because you don't have to differentiate anything. You can just transform it and you have an ODE. You can have an ODE and expand it out with some extra variables and it looks like a DAE, but it's the same thing. In this case, we have this algebraic loop. This is actually an index D of 1 because you can, in principle, differentiate these. So if you differentiate, you will get z prime, x and x dot here, y and y dot here. So you get more variables, and then you'll see that you can get an equation system and transform this into an ODE. This is not how tools are doing it, because it can result in instability. So typically when you have an index 1, to solve it in the way that I talked about before, that you go between the ODE solver and the algebraic solution. But this is basically why it's called an DAE1. There are some authors and some literatures you actually have a little bit slightly definition, and then it becomes not a 1 but a 2. But this is I would say the most common way that people think about this. So why do we care about this DAE and index? Well, we'll come to that because these higher index problems are not straightforward. You cannot just solve them with this technique. So you need to differentiate the equations symbolically to be able to come down to this index 1 to be able to solve it. And in practice, many like simple mechanical systems here, depending on how you connect them, becomes directly index 3. So they cannot be solved without doing this. So let's take another example here. This driving shaft that we looked at in the beginning. So here, if you would write out the equation system, you get something like this. We don't have to look at this, but it is a DA. If we would count the variables here, so we have these variables, and some of them appear differentiated. Now, you can write out this in it's called incidence matrix, and that we are going to use a lot here in the future, this kind of matrix. So this means that we have the equations on this side, and then we have the highest derivative of each variable. So you see here, we had in total here 8 variables, where half of them appear differentiated. So we show here the differentiated version, and then we have the other variables that are not differentiated, algebraic ones also here. So that's why these matrices becomes always square. Same number of unknown and variables. And the incidence matrix is basically just telling, does this equation contain this variable? Say equation 1 here. We see that F1 contains, or maybe this was actually not a transformation from this. F1 is probably one of the other ones. So omega 1.
Not the last
Or do I have a bug? It's the wrong matrix. Could be the wrong matrix. Actually, it doesn't matter because it's not the point of the slide. Is not that. But the point is that to be able to solve this, to be able to whatever solve this, that we need for each equation there must be a matching with a variable to be able to solve it. So it must in some way it must be a matching between an unknown variable and an equation to be able to solve it. And here was an example of this matching. Yeah, it's correct. F1 is this one. It's the 5. I think I just messed up the symbol there. This symbol. It's the wrong 5. omega and phi, but it's different. Okay, so there is a matching here. In this case, there is a matching. And if there is a matching, we can also perhaps sort them. We can change the order of the equations. You can always change the order. You can change the order of both the columns and the rows. And if you remember Gaussian elimination, what you want to do find is this. So you have everything as a triangular form, so you can then solve equation by equation, and then the rest is unknown. So then this case was actually index 0 because you can substitute and get the node redirectly in this particular case. So the matching is fundamental to be able to solve it. So the first algorithm that we're going to look at is the matching algorithm. How do you, from an incident matrix, find a matching? And if you cannot find it, it should return that you cannot find a matching and it's impossible to find such a matching. And it's complicated enough that we will not be able to just figure out the algorithm on the fly. Because this algorithm was not used for equation system, so it's just a graph algorithm. So we'll first have an example, then we'll give an algorithm. For this lecture, actually, there are 4 slides with algorithms that I'm going to go through and we're going to do exercises on. And they are fairly complicated, so you need to look at this. And I have put it on the web, so if you have your computer and network, you can get it. Because when I'm jumping between slides, then later on it's good to have it. That's on the web page. Okay, so that is example here. Now when I'm writing f of y, and here it means basically that this equation contains a y. This equation contains this. We don't care about exactly how the rest of the equation is actually structured. We're just interested if equation contains this variable. So this equation system we can rewrite in this incidence matrix, F1, F2, and F3. And as you see, x1, x2 appears differentiated. So that's why we just choose it. You see F1, F1, y, F2, x1, x2, and y, and x3. Then we can transform this into a bipartite graph. How many of you heard of bipartite graph? Right. So if you're taking some graph theory course lately, you probably stumbled on this. It's not particularly complicated. It's basically a graph. You have vertices and edges, but in the bipartite graph, you have divided the sets of vertices into 2 sets. That's basically the difference. So here we say F and V are 2 sets of vertices, and then we have the edges, E. So what this means here is that we say that the first set F here is the set of equations. So in this case, we talk about F1, F2, F3 as the different vertices. Then we have another set that is the set of variables, V, and that would be x1 dot, x2 dot, and y. So what is then E? Well, that is the edge saying exactly the same information as the incidence matrix, saying that F1, equation F1, contains y. That means that we have an edge from F1 to y. And this is an undirected graph as well. And you can write out the opposite order. I haven't written out in both directions. So you can visualize this bipartite graph. Typically, you write one set on one side and another set on the other side, and then you draw lines between them. So here we see f1 contains equation unknown y. f2 has three variables, all of them. f3 has just x2. Okay, so this is important to just understand these definitions, because the rest of this whole module will use these bipartite graphs and incidence matrix all the time. Okay, algorithm matching. First part, second part. And let's see here. I think we can manage soon. You have to fire up your laptops. So what it's trying to find here is an assignment. Basically modeled as this assignment, saying here that V is assigned to this function f. Otherwise, if it doesn't exist in this mapping, it's nil. So for a certain variable v, if this mapping contains that, it maps to this particular equation. So why have you v to f instead of f to v? Would it be, it's good to say that f points to this variable. So this is a mapping, this is a function. Any idea why? So the definition of a function is that
here we have multiple values in output from the assigned function.
so we can, one variable can point to only one equation, right? But one equation can contain many variables. So if we would do the opposite, we cannot have more than one variable in each equation. So that's why I have defined this mapping in this way. So this is just a definition of a normal mathematical function or discrete mathematical function. So now nothing is continuous here right now. I mean, the algorithm, we are just talking about pure discrete math, basically. Okay? So in the end, we want to have for each variable a pointer to a function, to an equation. And this should actually be a one-to-one, because we want to find one mapping to each equation. We are going to use this coloring visiting schema here. So I'm saying that there is a set of colored vertices, if there's a part of the set C, and that is part of the union of the equations f and the variables v. Should be both equations, both kind of nodes can be colored. So if they're part of C, then we say that it's colored. So this coloring scheme is used not right now. It's going to, when we use this later on, this matching algorithm for the Pantelides algorithm, then we will use this coloring. So you don't have to really care about this, but that is what it means. And also with this notation I'm using in all these equations. So these are published in different papers and different. So I've written up these equations in this algorithm in a specific style. So it's hopefully are clear. So I'm using this underline here to also to show that when we're calling a function and there can be a side effect, that is that this parameter that we are sending in can be updated by the calling function, then I have underscore. So you're thinking about like you have an imperative, if you're calling by reference basically, and you're changing it. To make it clear that these ones can be match equation here when that is called, can change C and a sign, but will not affect F or G and G. It's just a convention to make it clear. And as I said, this coloring and also this V map is not used in this first one to just do the matching. It's used when the matching element is used together with Pantelides. But instead of needing to recreate this matching function twice, it's already included. But you can ignore it right now. Okay, so we have the first task here for you. Exercise. You can keep track of C as well, but it's the assignment is the important thing. So you should basically try to follow this algorithm now and do the matching of this input problem. And then as output, we want to see the assignment. And the assignment is a function, a mapping, that will be like this. Sub equals, and then you say that maybe x dot 1 maps to f2, x 2 dot maps to maybe f1. That's it. In this form, the mapping. How is this mapping? Is discrete function defined?
I didn't get what is the assigned function when a variable is assigned to multiple functions. For example, x2 is assigned to both f2 and f3. So what the assigned function returns in this case?
So the assigned function in the end will just have a one-to-one mapping. So that's actually, so it was a little misleading perhaps in the first, because we are only going to have one variable mapping to one function in the end. That is what the matching algorithm is trying to solve, is to find is there a unique mapping between variables and functions. So, for example, it might be that, you say, assign this one to this one, and this one to this one, and this one to this one. Now that was not possible in this case, but then we have found match.
For the maximum.
Yes.
For the maximum.
Exactly, it's a maximum traversal. And we called maximum traversal or match. So this is a standard algorithm. So most of the algorithms I'm going to describe, basically except for Pantelides, are kind of standard algorithms in graph theory, but are used as a toolbox for solving. Okay, so I'm maximum traversal. Oh, it's just called the maximum. It's like in the Pantelides original paper, it's said as it also defined as just as a sound. It's not linear, but it's not correlated. I'm not pretty sure about the product complexity. It's a good question to know. But it's not that bad. It's not linear. So to be able to solve this, you need pen and paper. Otherwise, you cannot. Or an iPad that you can draw on. Do you have pen and paper?
No.
Either of that. We can look for my list paper that is here.
I just put to the front. But I will do it today, no problem.
You work with him?
Yeah.
You don't want paper?
Oh, that's fine, that's fine. No, 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 it's-
So here we go, we can match condition. So here's what we can match condition.
I'm sorry, is it possible that the execution never goes into the else clause? In this
The
case?
else of the match equation.
Because if I start with f1y, then I say, because if when you say there exists a v that equal gd and so on, the if is always, the first one is f1y, the second one is f2, and then I should find the first one, which is x1 dot. The third one would be f3 x2 dot, and it's done.
Right.
Yeah.
That is one possibility.
And so we never go into the else in this case.
Right. So if you ever started, you went first to f1 to y, and then you selected f2, but you took x2.
Okay, which one?
Could be. I mean, since it's arbitrary choice there, so it's should get a matching. If it turns out you should get a maximum matching. You should get a matching.
The else part of the match equation function is like a backtrack for.
There, yeah. It's recursive.
Yeah.
It's a recursive call to itself.
He removes some previous assignment and tries to. I got the idea.
Okay, when I pass assign B to the bottom, I'm passing 1F, which is different. Yeah. And so I try again another.
Should I sketch?
Yeah.
So we can start with this. I'm just writing it down again. Right. This one. And that. So the first thing that maybe a couple of you observed that depending on how you select this in an order, can turn out to be pretty simple in this case to find a matching. So in the first case, the F1 just went into the selected F, and then it picks something that is on the right hand side, a variable, such that it's not defined, nothing is defined in the beginning, and the V map is also null. So it means that we could first select this one, and then go up and take the next one. And if we, in that case, selected this one, and the time case selected this one, we were done directly. So that was the simple case. But as you see here, these, if there exist, this is how these algorithms are designed, that it's a non-deterministic choice of which you pick. Now we're not giving any correctness proofs here, but that is, there are for sure proven the correctness of this algorithm. That means that regardless of the choice you do, you end up finding a matching if it exists. But it doesn't mean that it will be the same matching. It can be a different matching. But if a matching exists, it will find it. And if it cannot find, it will never find it, regardless of the order. So in this case, we have this matching. We'll see here what happens if we instead, in the first case, it started with F1 again. There's just one choice. So it will find this matching. In the second thing, instead of selecting this one, we select this one. So we know that this one will fail. In this case, we go there, we go into the first case and assign x to f here, and we get this assignment. I'm not drawing it down right now. I can do like this because we will change it. Okay. Then we come here, take f3 as input here. We're coloring now, so now we're calling it f1, f2, f3. We should probably do that just for sake of reference. F1, F2, we're calling this one. And then in the final case here, we come here, but we see that it exists a variable v, that is x2 brick dot here. But the assignment here is not null because it's assigned to, already assigned to f2. Right? So then it cannot go into the, then it will go to the else branch. And then we say, again, for each of the variables v that f is pointing to, so in this case it's the same, x2, and v is not colored, which is not, we have just colored f1 and f2, then, and v map is nil, which is not, which it is, do the following. So we color v now we color x2, okay, follow, and we recursively call ourselves here, but we call with whatever v, and v was, remember, was x2 this time, is pointing to, which is f2, because we have already assigned that one, right? So we're calling ourselves again, but this time with f2. Okay, now we are here, so f here is f2. We are coloring f2 again, doesn't matter. Does it exist a variable v such that f, such as it's got a branching, where x is nil, and this is true, but this is true anyway. Is there? Well, in this case, one possibility is x1. Why is not a possibility? Because it's already assigned. This one is not a possibility because it's assigned by itself. So this is a possibility. Okay, then we go in here. And then we do assign x1 to v. So we assign this one now here. And then we return true. We come here back, and f, remember what f was in this case before we called it, what's on the stack there? Well, it's f3. Now we assign f3 to v, and v was in this case what that was pointing to. So in this case, we got the same result as other matching. So what it's doing when it's taking this path is it's time flipping it around and then tracking back. And it's absolutely not obvious why this works in all cases. But
because when it's going into recursively, C is filled up with the previous function, so it will never go on the same steps like before.
right.
That's so
Also.
that it will span over all over the places. And when it finishes, it will go up and up the first choice.
So it basically says that if you just get one matching failure, it will say that it will not match. So it will always return true or false if we found a match or not. In this case, both cases, it finds a match. You got a question about complexity here, and I'm not really sure. I mean, it's not. It's a little bit deeper thoughts about actually analyzing this recursively. But it's not. It's not square. Some log might. I'm not sure. Okay, so that's the matching function. I hope you got some intuition at least what it means. But real understanding, it's kind of the same for all these algorithms. They are complicated, so the proofs are not obvious. So it's okay, and that's what we got here. And here I also have the two cases here where we came to the same conclusion. Okay, let's continue here with the matching. By the way, let's see, was it 5 we're supposed to continue to, right? I think. 5. It's 4 now. Do you feel for a short break before now, or running on for 1 hour now? It's a bit long, right? Should we have a short break? Yeah, we'll take a short break. I guess you know that also when you're teaching, it's so easy when you're standing there and talking, you just forget about the time, and then it's like, and all about, when you're falling asleep.
It's a very interesting.
It's
Interesting.
yeah,
It's nice to know things.
it's I'm quite. I mean, the algorithms here are making a pretty good picture of what is happening.
In the compiler.
Then there are a lot of tricks there. I mean, people have invested many years in Python, so it's a bit more than this.
Faster, yeah,
Make it faster,
of
but it's a basic algorithm.
Yeah.
trasposti alla prima e F3 trasposti alla seconda riga, ci dovreste avere una cosa particolare. Sì. Quindi sicuramente poi di risolvere. Questo algoritmo trova la divisione tra le ma il gruppo di segno è quello di la sostituisce C'è un break.
To break. Dettaglio del solver.
Sì. Poi esatto, il lavoro forte del compile.
Quando è che parti? Dove vai a finire? A Sa. Scherano? Tu sei al terzo anno, il quarto anno, no? Hai finito al terzo anno, tutto il quarto anno, no, ora sei...
Sì, cioè, vabbè, ha fatto un paio di mesi.
Ti sei fatto vedere un po', per vedere un po'.
Sì, ce l'ho.
Mi sono, se senza so. Come? No, cioè, perché il problema importante è quello, no? Dai, buono.
Sì, sì, sì.
Poi il posticino dove lei, ma non so dove vai a finire, dove trovi casa.
No, lì,
Passa Cleo.
ho già provato. Sono 5 km.
Perfetto, sei in mezzo alla campata. Sei in mezzo, in the middle of nowhere.
Esatto.
In mezzo ci sono i campi di girasole e in mezzo ai campi di girasole c'è l'acceleratore e il sincrotrone del coso. Questo palazzo dell'università.
Sono attacchi sotto, sotto la foresta.
Io andai, ci usai come è stato? Quest'anno ho progetto alla fine. Ma era carino. Il posto c'è il posto poi dove lavorare è bellissimo. Nessuno.
Li chiamiamo poi i ragazzi che hanno partecipato. Li chiamo io nella stanza, mi faccio mandare da lui per bambina, sono quelle persone che c'erano, sicuramente la provvisionata delle persone che c'erano, ma a vista dal valore che sono 100.000. Sì, bisogna ricordarsi di lui che non te lo vedi tutti i giorni. Ecco. E poi la fare. Sì. Mando una mail con il suo nome, magari te lo mando lì, queste cose che fai, nominativo e convocato. Domani lui sicuramente lo farà mattinata entrare il corso, so che lo lascerà io. Non so se sono già preparato, andiamo, va bene, allora sì. Facciamo allora ricordandoli che hai partecipato al corso, così poi non capiremo mai infatti questo
But it's more about not these kind of information, more about analytics. I have a friend that did his PhD in control theory on GAs. That is okay. So let's continue. So we have this matching here, and this is basically how we then get these red squares when I showed the matching before. So we say that here in this case we will solve for y in f1, and then we will solve for x1 dot in f2 and so on. So there's a unique here. And now we, of course, we can always permute the matrices. So we can change the order here. F3, F2, change the order there, and also the columns. So then you can see that if we have, in this case, you'll see that it's not always that case, but we get the triangular form. So we can actually solve it straightforward in this case. So how do we get to this triangular form from this matching? We might find a matching here, and we can perhaps then sort it into this lower triangular matrix form, but it's not always possible to go into this lower triangular matrix form, because if we have that, it's straightforward to solve, right? So if it's just lower, it's just straightforward. We can always permute in a different way. So if we permute in this way, and if we cannot go to a lower triangular form, if we can go into block low triangular form, there are identified blocks that have loops. We have algebraic loops. These ones are then dependent on each other. So it means to be solved. But this one and this one is not. So it means that you can solve, and then there is a small algebraic equation system. So you can have a number of small algebraic equation systems that have an order. And for solving, that is much more efficient than try to solve everything as one big. Because you can basically have a very efficient code running, and then you have a couple of small, hopefully, blocks that you're solving. The problem is if the dependency makes that the small becomes the whole thing. And that is the problem, especially with 3D mechanics, when they are connecting together. So there are special techniques in these libraries to be able to cut these. Otherwise you get these big algebraic loops, which makes it very inefficient to solve. And these algebraic loops can then be, solved depending if they are linear or non-linear. If it's linear, it's use Gaussian elimination. Otherwise, there are different iterative methods like Newton's method to solve it. So these are more standard methods. If you get into this form, you can use standard numerical methods. So in this case, where we have this BLT form and we have it sorted into, but we have some algebraic loops. This is when we have this in the index 1 that I talked about before. So getting into this form, when we have the matching, this is what this BLT sorting is about. It's basically sorting into block lower triangle form. You can probably not see that because my computer is in the way. It says BLT sorting, part 3. If we take a look at this pendulum, so this is a classic example also for expressing a DAE, because it's fairly simple to understand and it's actually surprisingly complicated from a DAE point of view. And it's just complicated if we use Cartesian coordinates. If we use the unknown as the angle instead, it becomes just an OD. So, of course, it's not the best way to model a pendulum, but if you do it this way, you get a DAE that we can discuss. So it's just an example to provide an example for the DAE. So if we just look at the physical model here, we have T is an unknown is the tension in the string. And then we're basically using Newton's law here in X direction and Y direction. And we have mg here is the mass and the gravity. So the unknowns here are the second derivative of y, second derivative of x, and the tension. And this equation here, you see square of x square of y equals the square of the length of the pendulum. So it becomes a constraint that is what making the pendulum follow the trajectory. So we often talk about the algebraic constraints. And here clearly this algebraic equation here is a constraint. This is constraining the equation system. But the actual law of motions are in 2 equations. And they can be simplified. Just to make this a little bit easier to reason about, we simplify this. We say that tension divided by the length, we just use the lambda symbol. M, we just make it 1 here. And L2, we just use a big L instead. Makes the notation a little bit simpler. We got this, a bit simplified equation system. So we can rewrite it easily into first order. This we can just introduce u and v. And then we make the derivative of u instead. So we get rid of the double dots here. And why I'm doing that is that for Pantelides' algorithm later on assumes first order derivatives as input. So we can always transform it into first order derivatives by substituting here. You see here, x, after the u dot here will be differentiated in x 2 times and get the second derivative. So is this the DA? Yeah, sure. Can we solve it? Can we create a BLT sorting of it? Let's put out the incident matrix here for this one. So you have x, y, u, and v all appears differentiated. Just lambda that is not differentiated. Okay? And then we just plot this x here, y here, u dot here and lambda, etc. What is special about this?
Zeros.
Then-
Fine.
Right, we have variables here, but these are not unknowns, right? Because they, x and y, are not differentiated. And the only ones that are unknowns are the highest derivative. So they become zeros in these columns. And the matching problem was to find one unknown to each equation. That means that we'll have to find a diagonal here. We cannot do that. So this one we cannot solve. At least using these matching and then BLT. But if you throw this model like this into Modelica, it will gladly show you the pendulum. So how can it solve this? Any idea what you can do with this equation system?
Numeric.
Numerics?
Numerical.
Numerical? No, it's not possible.
We need to add another equation.
We need to get some more equations, right? And how can we get new equations?
Composing existing equations? No.
No, then we're not
Initial
interested.
state.
Hmm?
Initial state.
No.
Deriving something.
We can differentiate. Yes. We want to find this one. By the way, when we get this kind of problem where we cannot find a matching, if it's solvable in the end, it's a higher index problem. So the idea here is that we can differentiate equations. So if you differentiate this one, you will have x and x dot, so like 2x times x dot with this component. And you will get a y and y dot. So suddenly you will have these appear here. So you get more information. So this is what basically Pantelides is all about. Doing this differentiation in a minimal amount of time that you need to get into this form. There are also other methods called like price method, which is actually a little bit more intuitive. It's not very well, I know it's well known, but it's later. It's much newer than Pantelides, and it's not used so much in compilers in general. But it's got some nice properties, and also actually more, a little bit more intuitive. So it's more describing the difference between how far they are, and then they use a standard algorithm, graph algorithm to solve it. So it becomes a matching problem, but with a distance. But I'm not going to talk about this, but for those of you who are interested, this is a paper that can be interesting to read. But it's then you're diving into this area, really. But Pantelides, I'm going to talk about. And that is figuring out which equations to differentiate. So just saying how these algorithms are fitting together then. So we just talked about the matching algorithm. Then we have BLT sorting, Pantelides, and then we have this dummy derivative. So if we just take a look at how they fit together in a very quite simplified way. It's not always done exactly like this in nature. But if we have this matching, if we do that first, can we match? Can we find a matching? Because we need to do that to be able to solve it. If we have that, we can do the BLT sorting and get into this block lower triangular form. And if we have the lower triangular form, all the blocks are just of size 1. And then you have it perfect. Or otherwise, you get these algebraic loops. And then you get an index 1, which is also simple to solve. But if you cannot get the matching, you use the Pantelides algorithm to differentiate, decide what to actually differentiate. And when you decide which equation to differentiate and how many times, you can do this reduction of the index. You actually reduce it down to the index 1. And the classic thing is to do symbolic differentiation. You can also do automatic differentiation. But if it's not possible to find such a thing, then it's an error, and it will be said that this is a structurally singular matrix and it cannot be solved. And you can create such a thing, so if you're combining in the wrong way in the Modelica tool, and it will throw that thing. It's structurally singular. Not possible to solve. And typically that is because the Pantelides error then failed. And it could be fundamentally not possible to solve it. And if we go there, we come back to the BLT and we can sort it. And then we can have this index 1 DAE, and then we can use standard numerical solvers. Either combine it using a ODE together with a Gaussian or Newton's method for the algebraic part, or there's many tools are doing that. Or you can use a DAE solver, and the DAE solvers are basically stable on index 1 problems. And some of them are some specific constraints on index 2 or 3, but they are just special classes they can, which is out of scope. But then you can throw an index 1 DAE solver at it. And then it's kind of doing both the algebraic solving and in a little bit more hidden way. However, doing this exactly right now is not the perfect thing to do in a really complete toolchain, because when we are substituting and replacing equations with its differentiated versions, they are mathematically correct that since we're doing a numerical approximation, we get a drifting. So for the pendulum, it would mean that the length of the pendulum arm becomes longer and longer along its swings because of the numerical drifting problem. And then there is a solution to solve this. And one of the methods that is used in most tools is called dummy derivative. So it's a way to not actually replace the differential equations, but just adding them. So you get more and more equations when you differentiate. But then the problem is you have more and more equations, but you have the same number of unknowns. So then you get too many equations and you get over-constrained. And then the dummy derivatives is introducing new unknowns in the equation system in a way so it's still consistent and mathematical design. And then you remove the drifting problem. And that is so a correctly implemented tool do not have this drifting problem. So this is like an overview.
This means that Modelica always use equations. It does not do numerical simulations now, like matter that's
well, in the end, it must. This is equations reduces into an index 1 DAE. And then when you have the index 1, then you do numerical approximation.
Oh, okay.
You always do that in the end. Otherwise, you cannot get a simulation result. But since you have DAEs, you cannot just do it. Like Simulink, you have basically ODEs.
Yeah.
So you don't have this problem. But when you do this 8 causal modeling, you get DAEs. Because if you think about it, the sum to 0 are constraints. In the same way that the Pantelides, or the pendulum here, had the spring, the trajectory of the pendulum is a constraint. The Kirchhoff's law forms constraints on the variables. So this is oversimplified, but it's many tools are using, like the Modelica, for example, is doing in this similar thing. You can have some, for example, Pantelides is using matching. So typically you don't do matching and then Pantelides. It's kind of the first part of Pantelides is matching, and if it fails, the first matching it will. Pantelides uses matching many times. Part of it. So you do that, and then you go into BLT. I think there are also implementations where you cannot do Pantelides in parts of this equation system. That you combine these algorithms in some ways, but that is not the school book. There is no really reference how this fits together, not any paper, and that is really.
It's like more heuristics of the people who build the tool.
Right. So this is more my experience about this and in working in the field. Everybody says it would be great to write this kind of paper, but no one really has got the time to have done this. How they fit together. I think they are it's a little bit different in different tools as well. Okay, so that's the matching and how it fits together. So now the next thing is BLT sorting, getting into this sorted form. And the algorithm looks something like this. So there are some published publications. So this is one interpretation of it. So if you look at the book, you will not get exactly the same. So this is a reconstruction that I've done, which is basing on the method that one is using. It's actually the workhorse is Tarjan's algorithm for strongly connected components. How many of you say that you know Tarjan's algorithm, strongly connected components? A little bit, some of you. So this is algorithms classes. You quite often are taught this, but it's I mean, it's used in a lot of different things. Tarjan got basically, I mean, he's has done many contributions and got the Turing Award, the Nobel Prize for Computer Scientists, and this algorithm is probably one of the reasons. But we're going to go through it. Also. I mean, it was not used for this purpose. It's just computing the strongly connected components in a graph. So it's a very general algorithm. But for the whole BLT, say that you have an input is the bipartite graph G we had before. An output is a stack of sets of equation vertices, where each set represents an equation block in the BLT matrix. So you basically get a stack where you can transform into a list, and then that represents sets of equations, and each set is one block. And since the set, the order does not matter within that set, which is the same thing as in the algebraic loop. The order of the equations in the algebraic loop doesn't matter. But the order between these sets matters, because that's the order that you're going to solve it. So the output here is both that you get these blocks and you get an order. So you can show this in 3 steps. First, you find the matching, which was basically what we did before. Then you construct a graph, now not a bipartite graph, but rather a digraph, a directed graph. And in the end, we call Tarjan's algorithm strongly connected component algorithm. And output from this strongly connected components is this strongly connected components, and as a byproduct, we get a topological sorting of these components. And this topological sorting is the correct order for solving it as well. So it's pretty nice, and it's a fast algorithm. And I don't remember the complexity, but it's log something as well. Okay, so let's start with an example here to illustrate. So we have here an equation system, a bigger one, with functions and with equations and variables. And if we call in the first part here, we're just basically calling our matching algorithm that we did before. And if we cannot find matching, we say, oh, it's singular. And what would we do if this happens? Well, what we could do is to basically use dependencies. So then in this case, we get this result here. We get this assignment. So this is what we looked at before, the matching. We get a matching here if it works. Okay. In this case, we have this variable matching to this. We don't have to redo this. It's just trust that we found a match. Then we should construct this graph, because Tarjan's algorithm works on a directed graph. And just looking at this, what does it mean? So we have this matching here for x3 dot and equation f6. So this means that x3 should be solved in equation f6. And when solving x4, another example, we see that it's f1 here, that's the solving for x4, is using the values of x3 and y2. It's also part of that. So therefore, we see that f1 must be dependent on f6 and which more? One else? f6 and f5. Because they are solved in these equations that this equation is using. And the same thing here for f3, which is f3 dependent on? Can you see that?
F6.
F6. So then you see that we are going to create a directed graph representing its dependencies. So we want to have as vertices the equations and the edges showing the dependencies. And then we're going to find the strongly connected components, because if you see that we have a cycle, things are dependent on each other, then we have a strongly connected component. That is the definition of a strongly connected component. You can follow in the cycle. Then you will have a number of strongly connected components. So let's create D graphically. Here is the definitions of how to create this equation system, or the example. So your task now is a bit of an exercise here to wake you up. So try on pen and paper and create D. That is the output graph for this example. On paper, I think. Not this one. Your hammer.
Maybe.
That's the next one.
I have
You got it. Martin, when you talk about it, should be in two forms that are almost identical.
These are the ones that you're trying to fill in.
Yeah. Just filling that, and then I realized that it's the same one. Strange thing.
Now, here it says that if the information are already provided to the administration and did not change, then you only need to indicate the family name and name.
Okay. And I think sadly,
So everything else will stay the same as
surname. Where is my first name? Oh, it's only my son.
oh no, name and then surname. So David Roman.
They want to share.
Probably skip that. You don't have any fiscal rules, payments, there, I guess.
I should fill it in when I need it. And this one is also
The same statements. Did they explain this for avoiding double taxation?
right. I think what it is typically we have. I mean, I think it's in Sweden have the tax agreements in the US. So I'll probably pay the taxes here, and then they will not charge you over. I will not. I don't understand.
But if you pay the taxes here, they will pre-deduct 30%.
Right. So they will pay that.
Yeah, I think it's probably like.
It's simplicity.
Oh, so that is fine. Then you probably don't need this one. I don't know why you need this one. Can you give me those for a second? I'll ask for. Export this to me.
Okay, you got a solution? So I'm going to use this soon. Yeah. So the graph will probably look a little bit different how you draw it.
It's okay to fill in just one.
Okay, good. Okay, so this is the solution that I got. It's almost, the formalization here is kind of so obvious when you understand the idea that you just look at matrices and do this transformation. You got any question? Do you understand this for the formalization? Did you get similar result? Or, yeah. Okay, good. So then I will not go through it any further. So you can write it out here, of course, in this form, the more explicit form with each edge describing how they're mapped. And graphically it becomes it's the same. Okay. So this last step is then the Pantelides algorithm. And if we're ending at 5, I'm not really sure that we'll actually have the time to go through it. It's a little bit complicated. I think we should not stress it because we are ending at 5 on time. Yes. Well, so I can say some word about it, and then we'll do the actual exercise afterwards. Tomorrow, first. So this is the last part, and what we are actually preparing here is that we are calling this strongly connected component multiple times for each of the vertices. And there are 2 special mappings that exists when you are doing this transversal. You have the low link and the numbers. And exactly what they mean is not that easy to actually explain. So the easiest way to explain it is by we will take this example and try to work our way through the algorithm. And then you get an intuition what it actually means. But it's got some weird names, low link and numbers. But it's the way the algorithm works when it's doing a depth first search. So these are depth first search methods, it's searching the graph and then also coloring what it has been visiting before. So in that way it breaks the nodes, the cycles. Otherwise, if there were a cycle, it would go on forever. And his original paper is actually called something like Algorithms with Depth First Search, or something like that. And one of the algorithms that is presented in this paper is the strongly connected component algorithm. But it was more the principle of algorithms that are designed in this way, using the depth first search. That was the innovation. Okay, so it's the exercise is actually to start to do this algorithm with this example. But I don't think we can do that in 10 minutes. We'll start with that tomorrow instead. Other questions? Things we have learned today. So today we've basically been talking about the Modelica, beginning with the concepts. Then I've done some modeling, showed the principles, and now we're diving into the low end. The question for you is, or what part do you think is mostly interesting? Is this low end part or the high level part? Interested to get some feedback. What is the over
high level?
The high level.
But also having an idea of the internal working is important. So maybe not in that deep
Right.
details, but it's very, very nice to have an idea, for example, of how the various methods interact.
Right.
Some simplified view to show.
And I find it hard to explain these algorithms without going into depth in the end to really understand what it is. So just try.
I think that it depends really on the audience, on what the people are expected to move Modelica. Because if they are expected to just model a system, then the part is the most interesting, what happens behind the hood,
Right.
and also skip. Whereas if I need to try to derive an implementation from the model for doing transformation of the model or do code generation, then the knowledge of what is happening behind is also useful.
And that is basically what I'm find more display here.
Yeah.
Blocking. So I hope that you got some understanding. But we're going to go through the shortest algorithm tomorrow. And if you're not familiar with this, I think it's actually a really good algorithm to have the basic understanding of, because it's probably one of the most useful algorithms in general graph theory. Although it's not exactly its own use for this. So we'll spend maybe half an hour on that. Yeah, I think we'll end a little earlier if there are no other questions. Good. Okay. Thank you. No,
Break at the hotel.
1 5 o'clock.